chapter 12, and we talked about how to draw Lewis structures for covalent bonding. Remember, as we talked about, you do kind of want to follow those steps that we went over, as it will lead you to really probably a good structure. Again, you do not want to kind of do piecework where you kind of take each individual element together and try to put them together with the electrons. So really remember those steps are you basically want to figure out how it is put together, sort of the arrangement and how the atoms are put together. Remember to help you with that, usually it is the least electronegative atom in the center. That also means that hydrogen and fluorine are typically not in the center atom. Obviously, as we talked about, fluorine being the most electronegative, and hydrogen should only have 2 electrons, so it should never find itself in the middle. Otherwise, obviously, it'll have too many bonds and too many electrons as well. You then want to do the total number of valence electrons, and that is in the entire sort of molecule or ion that you are drawing. You also, if it happens to be an ion, you do need to adjust your charge or your total number of electrons based on the charge. So if it's an ion and it has a negative charge, you need to add those electrons into your total. If it's an ion with a positive charge, you need to subtract those from your total. Otherwise, again, you'll end up with pretty much too many electrons, too least electrons, if you don't do those things. Once you have the arrangement, you have the total number of electrons, which is important because that is how many electrons your picture has to have on the nose. You're just going to simply, again, as we talked about, just do a single sort of covalent bond to each of the outside atoms. And again, I'm going to start with just single bonds to the outside atoms. And obviously, at this point, each of those lines represent 2 electrons. You would subtract that off from your total number of electrons. And any remaining electrons that you have at that point, we always work from the outside in. And they do go on as pairs of electrons or dots. So we would go around, for example, and fill up each of the outside atoms until each of the outside atoms have 8 electrons, except if it's hydrogen. Obviously, it would get no dots because it should obviously be filled with 2. And you would just continue around to fill those extra electrons that you have. At some point, you will run out of outside atoms, and you probably will run out of electrons, perhaps. And if you do, then you need to look at your structure and make sure it's okay. If you fill up all the outside atoms and you still have electrons to put onto your picture, they then go to the center atom, and they also go on as dots of electrons. Once you get to the center atom and you're putting dots on it and you're out of electrons, you should pretty much have no more electrons to put on there. Once you do that, as I mentioned before, thank you, you want to check to make sure we have met the octet rule. Everybody needs 8 electrons, except for obviously hydrogen, that should only have 2. It's really at that point we talked about that if something does not meet the octet rule, that is really when you want to kind of deploy double bonds to fix it. If double bonds don't fix it, then you want to kind of go to triple bonds to fix it. Once again, you do not want to usually double bond or triple bond right out of the box when you're drawing these things. So let's just say, for example, here we didn't have any more electrons to, say, put onto that center atom. Obviously, that center atom would be short some electrons. Remember that when we make a double bond or even a triple bond, it works the same way. We cannot add any more dots or anything like that because we'll have too many electrons. We cannot just add the double bonded line or the triple bonded line because we will end up with too many electrons. So what we're doing when we do make, say, a double bond is we're going to take a pair of electrons and move them in to make the double bond. And that would yield us our picture here in my example. We would now be double bonded over here, and we would look something like this, I think. And here again, that maintains the correct number of electrons, and that again usually will fix your problem. If it does not fix your problem at that point, you should try any other double bond possibility if there is. If there's not another double bond possibility, then you need to go on to a triple bond to sort of fix it. Any questions on drawing that? Again, as I mentioned before, probably most things that you'll come across will have one center atom, but we did an example there. I think we did nitric acid at the end. It is definitely possible for things to have multiple central atoms. Again, you do the process very similar to what we do when there's just one center atom. Again, work outside and then come in. Again, the important thing to think about is, as I mentioned, you don't want to think about these electrons when you're drawing this type of Lewis structures as necessarily belonging to anybody in particular. You just want to think about sort of distributing the total number of electrons as evenly as you can, sort of across everybody that's within the molecular ion. Any questions on drawing Lewis structures? Yeah. All right, then continuing on here to wrap up this chapter, hopefully, maybe. We're going to talk a little bit about resonance. We did actually last time as well. But before we get there, let's talk a little bit about bonds and what happens with bond length and also bond strength. So this is a table of bond energy, I'm sorry, bond length. And you do not need to memorize these numbers or anything like that, but we're just going to use them to illustrate what we're talking about here. So if we take a look at carbon-carbon bonds, right here, that's our single bond, that's our double, and that's our triple. And when we look at the length between the two carbon atoms, in the single bond is 154 picometers, 133 for double bond, and 120. If we also look at the carbon-nitrogen bond, kind of single, double, and triple here, we see 143 for the single, we see 138 for the double, and 116 distance for the triple. What this illustrates is every time you sort of add a bond, the distance between the two atoms get closer. So, and that's because as you continue to add bonds, you go from a single bond to a double bond. You're putting a lot more electron density between the two atoms, and that's a lot more negative charge. And what that does is it brings those atoms closer together. If you make a triple bond, and again, putting a lot more that negative electron density between them, going to kind of drag them in closer to one another. So every time you add a bond, the distance between the atoms gets shorter and shorter, and they get closer and closer to one another. And this has a very big impact on strength as well. And in terms of bond strength, typically speaking, a triple bond is stronger than a double bond, and a double bond is stronger than a single bond. And that does correlate to our length here. Again, the smallest distance between the two atoms are in that triple bond, and they're much, much closer together. The way I think about it is if you get like a brand new pencil like out of a box, you can snap that thing, no problem, right? You just snap it. You take a chemistry test and all you got left is like a nubbin of a pencil and like a little eraser, right? Very hard to try to snap that small little pencil in half, right? It's held together really stronger. And that's sort of what happens here. As you keep adding those bonds, everybody gets closer. The bond gets stronger because everything is really compact together, and there's a lot more of that negative electron density between the two atoms. It makes it much harder to kind of get them away from each other or try to break those types of bonds. Now, a triple bond is not like 3 times as strong as a single bond or anything like that, but that is the general trend. Double bond is stronger than a single, and a triple bond is stronger than a double. Any questions on that there? Now, resonance structures, since we sort of touched upon it earlier, not going to go into great detail on it, but resonance structures do develop, as we saw earlier when we were drawing, I think, carbonate and a couple other ones, where you do get sort of an option as to where you could place that double bond. And if you remember, sort of in carbonate, we got to this point when we drew it, and we were short electrons on the carbon. Now, in this case, all 3 of those oxygens are pretty much equivalent to each other, and we could have put a double bond at any of those oxygens, once again, like we talked about, by just bringing those electrons in to do so. And because of that, we really could have drawn 3 equivalent Lewis structures for carbonate. One where we have, obviously, the double bond here up in the top. We also could have done it to the right, to the left as well. And they're equivalent structures because, as I mentioned before, what's really happening with those double bond electrons are they are what are known as being delocalized, which means at any given point in time, they may be associated with the top oxygen, they may be associated with the oxygen to the right, or those electrons may be sort of associated with the oxygen on the left. And that does give you, as I mentioned, an opportunity there to draw 3 different Lewis structures for it, as you can see here. And we have, again, our double bond over here in the top. We could have double bonded here to the left, or we could have double bonded to the right. And any one of these individual structures are perfectly fine if you were just, again, asked to draw a Lewis structure for carbonate. You could lay up any one of those 3 structures would be fine. And again, what's happening here is those electrons, are sort of moving around. So they could be anywhere in between as well. So the true structure is probably some version of all 3 of those sort of mixed together. But we can draw what's known as resonance structures. Usually we'll have these arrows. You don't have to worry too much about the negative charges here. That's actually why it's -2. Each of those oxygens actually have a negative charge, and that's what gives it a overall negative charge. Benzene is something that you won't see too much until you get to organic, but the benzene ring is basically all carbons. These are all carbons, basically, all the way around. And it also has 3 double bonds in it. So usually they don't put the carbons in. So this is benzene with 3 double bonds. Also, you could draw a resonance structure where double bonds are in the opposite location. And some people will actually draw benzene to indicate that those electrons are moving around. You'll sometimes even see just like a little circle drawn in the middle of it, and that indicates that those electrons can kind of move around, and double bonds could really be anywhere along the way. You definitely don't have to worry too much about benzene at all for this class, or probably the next class, couple of classes as well. All right, so that's good on resonance, I think. All right, now we've talked a lot about, obviously, in this chapter, the octet rule, and that's really, again, what the goal is for everybody when they are doing bonding. And really, the purpose behind that, as we talked a lot about, is the whole goal of bonding is for everybody to achieve the same electron configuration as the noble gases. And since the noble gases are group 8, they want 8 valence electrons like the noble gases have, which make them a nice stable situation. But there actually are some exceptions to the octet rule, although in this class we will never go over any of the exceptions or have to draw any of the exceptions to the octet rule. You do need to be aware of what the 3 exceptions are, but everything here will obey the octet rule. But in reality, there are a few different exceptions to it. One exception to the octet rule is actually what is known as an incomplete octet. There actually are some elements that are perfectly happy with less than 8 electrons. Probably your most common one is boron, aluminum as well, and beryllium. But boron is very common, the one that you come across the most in this exception. And boron is all good with like 6 electrons. It doesn't really look to need any more. Beryllium and aluminum usually will be more of a ionic sort of bonding, but it's sometimes used as an example, beryllium here with the hydrogens. But again, it only needs 4 electrons and stuff like that. So an incomplete octet, pretty much boron is usually the most common one. Again, could have less than 8 electrons. Another example of an exception to the octet rule is a odd electron molecule. And odd electron molecules are ones where they have an unpaired electron. And as you can see here, you're going to end up with an unpaired electron. That's also sometimes very much referred to as free radicals. They're ones that have unpaired electrons. Because of that, usually they're very, very reactive. A lot of atmospheric chemistry involves chlorine where that happens. And because they have that sort of unpaired electron, they want to kind of fix it in a sense. And it makes them very, very reactive. So it is possible, even though most of everything that we will see will come up with a nice even number of electrons, so nobody's unpaired. It is definitely possible to have sort of an unpaired electron, which is possible. Now, the last exception to the octet rule is the one that you will probably see the most when you go to the next class, not in here, but in the next class, the one that you'll see the most is the expanded octet. And much like there are some elements that are okay with less than 8, there's actually elements that are also okay with more than 8. They could have upwards of 10 to 12 electrons around them, and that's what's known as an expanded octet. And if you look at the periodic table where we find our friend sulfur, and you go a little bit to the right, a little bit to the left, and down in the non-metal region, these are all the elements that have the ability to do the expanded octet. Now, how can they do the expanded octet? It's pretty straightforward in the sense of if we look at the periodic table where sulfur is sitting, that is on period number 3. And that correlates, as we talked about in electron configuration, to an n is equal to 3 energy level. And on the 3rd energy level, what orbitals first begin to appear? Those are our d orbitals. Yeah. So because these guys are on the 3rd energy level, they actually have d orbitals available to them. Even if they're not using them, they do have them available to them. And that's where they can kind of store all the extra electrons because they have those extra ton of d orbitals available and they got a place to stash all those. So something like sulfur can go up to like 12 electrons in certain situations, and they're perfectly fine doing that because of that. That also means, by the way, just for future reference, not in this class, but if you go below that where like, carbon, nitrogen, oxygen, fluorine is, that is the 2nd period on the periodic table, which is the n equals 2 period. And on the 2nd energy level, there are no d orbitals available. There's only p orbitals. And that means they can never, ever go over 8. So those kind of above sulfur on the periodic table could never go over 8 because they don't have the d orbitals available to them. Those technically where sulfur is and down and to the right where our nonmetals are can go over 8 because they do have that. So you can have something like SF6, which if you draw the Lewis structure for it, will look something like this. And I'm not going to put the dots around the fluorine, but all those fluorines would have dots all the way around them. Did I get 6 on there? 1, 2, 3, 4, 5, 6. I did. And if we look at just the bonds between sulfur and fluorine in this case, you will see that we have 2, 4, 6, 8, 10, and 12 electrons around sulfur, and that's perfectly fine in that particular case. So you will definitely see this in the next class. There's a whole bunch of geometries and stuff that you learn, and that's the common exception that you see a lot in 1A. But here again, we will all obey the octet rule in this class, but you do need to know with 3 exceptions. This is also why when you look things up, perhaps on the internet or whatever it may be, you may not be given the answer you think you should be giving. Because if you're in a class like, say, us here, where everything will obey the octet rule, when you go to draw something like sulfate here, that has 6 for the sulfur, 6 for the oxygen, and there's 4 of them. And that -2 charge means I'm going to add to 24, 26, 32 valence electrons. You follow our rule here and you put your guys around. You do your 1 bond, 2 bonds, 3 bonds, 4 bonds. That is 8 electrons. We keep going 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. We look around. Everybody has met the octet rule, and this is actually a Lewis structure that you should get by following the octet rule. But if you search sulfate online, they're going to lay you up most likely this picture. Where you can see that the sulfur has done its expanded octet, right? And now your instructor is going to know for sure you looked that up because, he just told you many times not to go above the octet rule, and you're just obviously cheating yourself out of the education and copying the stuff from the internet, yes? So make sure that you don't do that. But actually, in this case, why you see this is for other reasons we don't talk about in this class that you will talk about in the next class. Believe it or not, this is actually the better structure than you get here. for some reasons known as formal charge and stuff like that. But that's why you see it like that. But obviously that is an expanded octet versus obeying the octet rule, which is the one on the left in this case. Yeah. Uh, they're actually not. So you can draw, and again, we don't get into it in this class, but you can draw, multiple Lewis structures, and you can use something that's known as formal charge that you're going to learn about in the next class to help you decide what is like a better structure than something else. And it could happen in a situation like this. These are two sort of acceptable structures for sulfate. If you're looking at formal charge and which one would be classified as like a better Lewis structure, really the one on the right there with the expanded octet is actually the better structure because it actually minimizes the formal charge on each of the elements there. So instead of all these guys here being like minus, all these guys having like a -1 charge, all these oxygens, and like the sulfur in the middle has a +2 charge, which is a relatively big what's known as a formal charge. You minimize pretty much all these guys to zeros, no charge, and just the -1 charges on the outside, and that makes for a much better structure based on sort of what's known as formal charge. But these are not really considered sort of resonance structures of each other. Because there's kind of two different versions of it. This is also why we drew CO2 the other day, right? I think when we did carbon dioxide. And we ended up with CO2, for example, with a double bond on both sides, right? And when we were doing the process of like making the second double bond, right before we did that, we had kind of a single double bond on one side or one double bond on that side. And we still have the single bond. Now, some of you might have thought, well, couldn't I just like maybe lay up a triple bond instead of double bonding the second side, right? And you could, and you would end up obviously with a structure that looks like this. And now it still has 2, 4, 6, 8, 10, 12, 14, whatever, how many electrons it's supposed to have. But when you do kind of the same thing, if you look at it based on formal charge, this is a much worse of a Lewis structure than this one is here. And for the same reason, it minimizes the actual individual charges on each of the elements within that molecule, and it makes it for a much better sort of structure and more stable in that way. On the left there, everybody's pretty much zeroed out. On the right, you got some like minuses and plus type charges that happens to be on each of those individual elements and doesn't make for a best structure. So that's why when we talk about earlier, like if you have the option of maybe double bond again, like we did there in CO2, it's probably what you want to do is kind of exhaust all your double bond options and then go into triple bond. And that usually, when I say will lead you to like a pretty good structure, what I'm talking about is sort of really the formal charge. It usually will get you to the right structure. There are some situations like sulfate where you will probably end up, if you're looking at formal charge, not the best structure, but it's still a good structure in terms of it. So it's kind of like best structure, better structure, okay type structures when you're kind of using that to help you decide. And that's why, again, some cases why you might wonder why we just don't triple bond it instead of like double bond it and stuff like that. Other questions? All right. And again, you'll talk all about formal charges when you get to the next class for sure. All right. The last thing we're going to talk about, or one of the last things we're going to talk about here in terms of bonding, is geometry and molecular geometry. And these are sort of the shapes of the molecules. And when we look at molecular geometry, we can sort of predict what the three-dimensional sort of shape of the molecule will be, or ion, based on really the Lewis structure in a sense of you draw a good Lewis structure. We always look at really the center atom. So when you're doing geometry, really the most important atom and the only atom you should look at is the center atom. And it's all about really two things when you look at the center atom. These are really the two things you're going to kind of look at, which is the number of electron pairs around the central atom and the number of bonds around the central atom. So those are the two main things that we look at to try to help us determine what the geometry of the molecule is. Once again, if you have multiple center atoms, you would do it for each center atom individually, but most of the things we'll see will have one central atom. And based on that, it'll tell us some geometries, and that's sort of the three-dimensional arrangement of the atom. Now, this is based on the idea that basically bonds are made up of electrons, right? And when you do that, you're going to have electrons near each other at some point. And as we talked about previously, because electrons are negatively charged, when electrons get near each other, they technically don't really want to be near each other because they have the same charge. They repel each other. So what they're ultimately trying to do, and what ultimately happens, is they are essentially trying to get as far away as possible from other electrons. But they can't completely leave because they're all being bonded together, right, and sharing electrons. So what happens is, as they try to move away from electrons, the molecule and those atoms that are there start to actually move as well. And that's what gives us some different shapes that happens as these electrons try to get away from one another, and they can't completely escape. But if there's a bonded atom, that atom that's bonded to those electrons are going to also move with them as they kind of move around and try to get away from one another. So this molecular geometry, or geometry of a molecule, is what's known as VSEPR, and it stands for valence shell electron pair repulsion model, hence the abbreviation. And it accounts for sort of the geometry that we see. Now, we are going to talk about two types of geometry. We're going to talk about what is sometimes referred to as the electron pair geometry. And that is the arrangement of electrons around the central atom. It doesn't matter if they're bonding electrons, non-bonding electrons. That is the arrangement of just how the electron pairs are around the central atom. For the rest of this little talk here, I'm just going to refer to that as EP, so I don't have to rewrite that whole thing out every time. And the other type of geometry that we're going to talk about is the molecular geometry. And that is also sometimes referred to as the shape of the molecule. And I'm just going to call that MG as we kind of go through our little lecture here. And that is taking into account all the electrons that are present and what types of electrons, how many bonds, and the overall shape of the molecule. Now, both of these things are going to basically be names. So these are going to be names that correspond to particular geometries. And as we will see, in some cases, the names will be the same. And in some cases, the names will be different depending on the situation. But sometimes they will be the same. Now, this is basically broken up into two types of molecules that we come across. One where there are no lone pairs on the central atom. So that means when you draw your Lewis structure, you basically have no dots on the central atom. And then the other type of molecules are ones where there are lone pairs. So when you draw your Lewis structure, you will at least have some dots on the central atom. So you got some dots on the central atom. Now, probably the extremely most important thing to remember is when you are doing geometry, and only when you're kind of doing geometry, this right here is the most important thing. It does not matter when you're doing geometry if you have a single bond, if you have a double bond, or if you have a triple bond. It does not matter. Everything counts as one. So they all count as one electron pair and one bond. So that is probably the most important thing as you go through and sort of count up everything. Everything counts as one. If you got two pairs of dots, counts as one electron pair. You got a single bonded line drawn, one electron pair. Got a double bonded, two lines drawn, one electron pair, one bond. You got three lines drawn for a triple bond, one electron pair, one bond. So everything counts as one. Again, only when you're doing geometry. So that's really important as you look at your Lewis structures. The other one is not so important because we're not going to deal a lot with resonance structures, but if you could draw any resonance structure you want, you could apply it to any of the structures you draw. You will end up in most cases with the same geometry regardless of, for example, regardless of which carbonate picture you took out of those three, you'll end up with the same geometry, so it doesn't really matter which one you apply it to. All right, so let's just start with really the simplest molecules you could have, and that is a diatomic molecule. And a diatomic molecule basically means there are only two atoms involved, which means you got this, basically. Now, when you only have two atoms, there is no central atom, so there is no atom in the middle. The only way you can arrange two atoms is a straight line, right? It's the shortest distance between 2 points. Straight line is basically. So the geometry is a no-brainer when you have this. It is always linear. Just put linear down and move on. It doesn't matter if those two things are the same atom or element, single bonded. Doesn't matter if it is two different elements together, linear, linear. Doesn't matter if it is a single bond or a double bond, still linear. Doesn't matter if it's a triple bond. It is still linear here. So all these guys are linear. If you only have two things, two of the same elements, two different elements, there's only one bond, two atoms. The geometry is always going to be linear. It doesn't matter, again, single, double, or triple. That's the easy one. Now, when it gets to three or more atoms, you do have to look at the central atom, and again, that is the most important thing. So let's talk about three or more atoms here in the geometry. The first example is beryllium chloride here. And once again, the most important thing is the central atom. So you want to always look at the one in the middle, and that is the most important thing. And the two things that you really want to count up is the number of electron pairs around that central atom and the number of bonds. And if you do that, let's take a look. That is one electron pair there for that line. That is two electron pairs there. And what we see is two electron pairs. It also has one bond and two bonds, right? So it's got two bonds there. Now, first off, electron pairs around the central atom is what determines what is known as the electron pair geometry. I said I wasn't going to write that out, so let's go EP next to it. And in this arrangement, because you only have basically two electron pairs, what happens is they decide, I'm just going to go opposites of each other. So they get as far away as possible. They go on opposite ends of a straight line, and they end up with a geometry known as linear. And again, basically those two electron pairs are going way away from each other as far as they can. Now, because of that, because these are bonded atoms, those atoms are going to move with those electron pairs, and they end up in the exact same geometry as the electron pairs, which is the molecular geometry here would be linear. So for something in this situation, both the electron pair geometry name and the molecular geometry name is linear. It has a bond angle of about 180 degrees. So as that separates out from each other, you're going to end up with a bond angle of 180 degrees. The bond angle, by the way, corresponds to the electron pair geometry name. So however many electron pairs there are, that's where we get our bond angle in this particular case. Any questions on that one so far? All right, the next type of geometry you come across is something with a central atom and three things attached. So once again, we're going to look at our central atom here, and maybe draw it a little bit better here. We'll kind of do it like this. All right, so looking once again at the central atom, the number of electron pairs around the central atom is 1, 2, and 3 electron pairs. Each of those lines represents an electron pair. So that is 3 electron pairs. When you have something that has 3 electron pairs around the central atom, the electron pair geometry name is what is known as trigonal planar. Some people will call it triangular as well. And when we look at the number of bonds here, there's 1, 2, and 3 bonds. And what happens in this case is those electron pairs are going to want to get away from each other. But As they start to move away, these guys are going to move away from each other. These guys on the bottom now, because there's that extra sort of electron pair and bond, they can't get too close to each other either because they do not want to be near each other as well. So they kind of move away from the top one, but then those bottom ones can't get too close. So they got to kind of find a happy medium where they're happy getting away from each other. This is why it's called triangular, because they basically end up in like a triangle sort of fashion there in terms of how they separate out from each other. Now, because these are all bonded atoms, the atoms will move in the exact same location, and the molecular geometry in this case will also be trigonal planar. So both the electron pair geometry and the molecular geometry in this case is the same name. They're both trigonal planar. They have a bond angle of about 120 degrees. So we got a bond angle of about 120 degrees happening here, and it makes, again, this sort of equilateral triangle as they arrange from each other. Any questions on that one there? Looking at the next sort of geometry you'll be responsible for, you will end up with a central atom that has 4 things attached, and that's pretty bad there. Let me just fix that up there. So it looks something like this. And there we go. All right, so our number of electron pairs, once again, always the center atom is the most important thing to look at, and the only one you should look at when you're doing geometry. We have 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. Something with 4 electron pairs around the central atom, its electron pair geometry name is known as tetrahedral. Now, the same deal is happening here, but now we have like an extra sort of atom there and electrons. We have, in this case, 1, 2, 3, and 4 bonds around the central atom. And its molecular geometry name will end up at tetrahedral as well. So in this particular case, what happens is, I do it a little bit like that. You got these electrons trying to spread out from each other, these guys as well. But again, with that 4th sort of electron pair and bond there, these guys again cannot get so close to each other. So they're going to kind of spread out in this arrangement. And we will end up with the exact same name for both of those. Once again, because they are all bonded atoms, the atoms themselves move in the same location as the electron pairs, and we end up with the same name for both of them. And it has a bond angle of 109.5 degrees is the bond angle in this case. Any questions on that one there? Now, this makes sort of like a triangle on the face of it, and almost like a pyramid sort of towards the bottom of it when you look at it. Now, up until this point, both of the names have been exactly the same. And the reason for that is, as I've been mentioning, there's really only dealing with one type of electrons here, and we're only dealing with bonding electrons. So when you look at the central atom, on all of these, there are no dots on the central atom. And when you ever draw a Lewis structure when there's no dots on the central atom, both of those geometries will be exactly the same. The electron pair geometry and the molecular geometry name will be exactly the same because they are bonded atoms. So as those electron pairs move, so do the atoms move exactly with them, and they end up in the same geometry location. So name will always be the same. When you start to introduce non-bonding electrons on the central atom, that is where we start to see the names start to be different. And the name that ends up being different is the molecular geometry name. The electron pair geometry will be the exact same. So if you got like 2 electron pairs, it'll be linear. If you got 3 electron pairs, it'll be trigonal planar. You got 4 electron pairs, it'll be tetrahedral. But because there's now going to be some non-bonding electrons involved, the geometry of that molecule will actually change because of it. So let's talk about why that happens. So when we look at electrons and how they interact with each other, there's like various degrees of that's okay and 2 degrees of wow, I really do not want to be near you in terms of electrons. So the best sort of situation in terms of repulsion is what we've been talking about, and that is bonding electrons near bonding electrons. So basically lines near lines, yeah, when you draw your Lewis structure. So when you have bonding electrons near bonding electrons, it's like kind of manageable in terms of we really don't want to be near each other, but we're not going to try to run super far away from each other. We could kind of live being near each other. The next sort of best situation, getting worse, is when you have non-bonding electrons near bonding electrons. So when you have dots near lines on your Lewis structure, those two things don't really want to be near each other. They're going to try to get away a little farther. The reason they could actually get away a little farther is those non-bonding electrons don't have an atom attached to them. So it has a little bit more room to kind of spread out because we don't have that extra atom in there. We have lost an atom from the bonding one, and it has a little bit more room. The worst situation in terms of electrons being near each other is non-bonding electrons near non-bonding electrons. Dots near dots is the worst situation. They will get as far away as possible from each other, and they're able to do that because neither one has an atom kind of to hold them down. So they have a little bit more space to kind of spread out and get away from each other. So as we introduce non-bonding electrons, because they're kind of not having that atom there, they have a little bit more space. So as they move away, anything with a bonded atom will also move away a little bit more, and we end up getting a different molecular geometry than we had when we had all bonded atoms together. So whenever you do see dots on the central atom, the electron pair geometry name and the molecular geometry name will be different names, and it's only the molecular geometry name that really will kind of change from what you expect. All right, so let's take a look at an example of that. Let's take a look at sulfur dioxide here. And we drew it earlier. If you draw sulfur dioxide correctly, it will look something like this. And once again, no other atom is important for geometry other than the one here in the middle. So that again is the one that we want to look at. So when we look at this, the number of electron pairs in this case is how many in this case? There is one electron pair there. There is two electron pairs there. It doesn't matter if they're dots or lines when you're counting them. And what about my double bond? It counts as how many? It only counts as one. So again, that double bond only counts as one. So there are only three electron pairs here. Now, the electron pair geometry name, which is based on that, is still the same as we saw earlier. So earlier we saw something with three electron pairs is trigonal planar. So that still stays the same. But now when we look at bonds, the number of bonds here on the central atom, there is one bond and two bonds. So again, the double bond only counts as one bond. So there are only two bonds. So what happens in this case is these non-bonding electrons are going to try to get away from those bonding electrons because they hate each other. But what happens though is as that is occurring, that's going to move those oxygens down, which unfortunately can't get too close to each other either because they're still electrons and they don't want to get too close to each other. So we're going to get this kind of separation happening here. And the molecular geometry name that happens is what is known as angular, is what we will go with. I will be honest with you, a lot of books and people will call this bent, or sometimes people will call it bent angular. We are going to roll with angular in this class, and I'll explain to you in just a bit why we're going to go with angular for this particular one. And it really has to do with the bond angle in this case. The bond angle is based off of the electron pair geometry. And if you remember, trigonal planar had a bond angle of 120 degrees. This will have a bond angle of less than 120 degrees. So just slightly less than it. But again, they're going to kind of fold down those oxygens as they get away from those non-bonding electrons. But once again, they can't get too close to each other because they got to kind of keep some distance. So it kind of ends up with this kind of angled type of geometry that occurs. Any questions on that one there? Next example is ammonia, which actually came out good on this picture, so that's good. So ammonia here, once again, looking at the central atom is the only thing we're concerned with. The number of electron pairs in this case, once again, one electron pair there, 2, 3, and 4. So when you're counting electron pairs, it doesn't matter if they're dots or lines, everything counts as one. So that means the electron pair geometry name for 4 electrons, as we saw earlier, is tetrahedral. But what happens in this particular case is those non-bonding electrons and bonding electrons are going to try to get as far away as possible. But because we do have those 3 bonded electrons and atoms, they also got to keep a little distance from each other. And what ends up happening is the molecular geometry here, because it has 1 bond, 2 bonds, and 3 bonds, that is the number of bonds here, which is 3. The molecular geometry ends up being what is known as trigonal pyramid. And this has a bond angle of less than your traditional tetrahedral bond angle of 109.5 degrees. So it's got about 107-ish on the bond angle on this one for real, but less than 109.5 in this particular case. Now, this is an important distinction. Something with 4 electron pairs and 3 bonds, its molecular geometry name is trigonal pyramid. Something with, like we saw earlier, something with 3 electron pairs and 3 bonds, its name is trigonal planar. These are different names, these are different geometries. You do need to specify which one you are talking about. You cannot just lay up trigonal and let me choose, because I'm going to choose an X. Yeah, so make sure you choose either planar or pyramid, and don't just write trigonal. Or my other favorite one, which is you're very confident with trigonal, and then you're confident with the P, and then maybe your writing gets really bad at the back end there, and you're like, it was planar, right? Because that's kind of what I wrote, or maybe it's like pyramid or something like that. I know it starts with a P. So make sure you do choose, because they are different geometries. They have different bonds, different numbers of electron pairs, and stuff like that. The last geometry that you are responsible for, which I'm not sure where it went to, so I'm just going to do it right here. I think it's on your notes, but on my handout it went somewhere. Is one like water. So we'll take a look at our friend water here. So if we take a look at water, once again, it is the central atom that is the most important. So we're going to look at the oxygen here. And the oxygen, in terms of number of electron pairs, in this case, 1, 2, 3, and 4. So once again, with 4 electron pairs, the electron pair geometry name is going to be tetrahedral. Now, in the case of water, you pretty much have all of the worst interactions happening in terms of electrons. You have bonding electrons near bonding, you have non-bonding near bonding, and you have non-bonding electrons near non-bonding electrons, dots near dots. That is like the worst case scenario. In terms of bonds here, we have 2 bonds. So what happens in this particular case because of that is we have these non-bonding electrons that are going to try to definitely get far away from each other as possible. As they're doing that, those bonded electrons that have the hydrogens will also try to keep some distance. But once again, they can't get too close to each other as well. So this ends up in the molecular geometry name known as bent or V-shaped. Yeah. And this is why we are going to be using angular for something like SO2, because angular's bond angle is less than 120 degrees. This bond angle is less than 109.5 degrees, about 104-ish or so for water. So it's a lot less of a bond angle than what you see with SO2. So that, again, is why we're going to use angular for that one and bent for sure for this one. Everybody uses bent for this one. Nowadays, not too many people throw the V-shaped in there, but it is bent or V-shaped is those. And that's why you typically will always see water a lot of times drawn like this in this bent or V-shaped sort of fashion when they kind of draw it because of the geometry that is here. Any questions on that? Best thing to do on this is, frankly, memorize. Yeah. So most people can't visualize a three-dimensional sort of space in their head. I can't either. The thing you want to do is there's a table online on Canvas that I made, and there's also a table in your book. You want to remember number of electron pairs, number of bonds, and the corresponding geometries for each of those is just really the best way to kind of do this. And here is that table. Whoops. Actually, this table I think is from your book. This table is from your book there. And basically, this is our number of electron pairs, right? And this is our number of bonds. So basically, these two columns here are what kind of what the table is. And then you have your electron pair geometry and your molecular geometry or shape name that you need. You need to insert in there the SO2 example is what you also need to pop in there, that angular one as well. But again, that's really probably the best way to know it. They do want you to know the bond angle here at the school, so you need to know the bond angles that go with them as well. Any questions on geometry? So just to show you how it works, we take a few that we did earlier and we drew. We obviously drew this earlier on in this chapter. We drew obviously this guy here. We did this guy. We did obviously this guy. We did this guy. Yeah, I think we also did this one here. All right, so let's just go through and just determine the geometries here. So first off, if we take a look, again, always the central atom. So looking at this guy, number of electron pairs on this guy is how many? There is one for that, 2 and 3. And number of bonds in this case is 1, 2, and 3. So again, something with 3 electron pairs. The electron pair geometry is going to be trigonal planar. Our molecular geometry, because there's no dots on the central atom, both names are going to be the same, right? So it's going to be trigonal planar as well on that one. This one we actually did in the example there. So once again, central atom, 1 electron pair, 2 electron pairs, 3 electron pairs. So 3 electron pairs, 1 bond, 2 bonds, 2 bonds. So again, our electron pair geometry going to be trigonal planar. Our molecular geometry, in this case, because there are dots, tells us we're going to have a different name. And because of that, with 2 electron pairs, 3 electron pairs and 2 bonds, our molecular geometry, as we talked about earlier, is going to be that angular one here. We'll come down here, we draw it down here maybe just to see it better. Central atom right here, we have 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. Only 1 and 2 bonds in this case. So our electron pair geometry is based on the number of electron pairs, and that is 4. So that's going to give us a tetrahedral electron pair geometry. Our molecular geometry, because it has only 2 bonds, is going to be pretty much just like water that we just talked about. Those bonding electrons are going to go down, the non-bonding electrons are going to go up and out, and you're going to end up with bent or V-shaped. Yeah. How about here? How many electron pairs on this one? There's only 2, 1, and 2. Number of bonds here is 1 and 2. So 2 electron pairs, 2 bonds. 2 electron pairs tells us our electron pair geometry is linear. And our molecular geometry will be the same because there are no dots on the central atom. So it'll also be linear as they both try to get away from each other. How about here? Our geometry here should just be linear because that's a diatomic molecule. There's no central atom, and that's the only way you could arrange that is a linear geometry in this particular case. And lastly, here, looking at this one, we have 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. And in terms of bonds, we have 1, 2, 3, and 4. It's got 4 bonds. Going to give us an electron pair geometry name of tetrahedral. Molecular geometry name will be the same as there's no dots. They're all bonding electrons, which means the atoms will move the same as the electrons and will end up the same. Any questions on how to identify that there? Got it. So obviously you need to be able to identify both the electron pair geometry name, the molecular geometry name, and you need to know the bond angle. Obviously you need to be able to draw a proper Lewis structure as well, yeah, along the way there to do all those things. Any questions on geometry here? The last thing we're going to talk about is clearly what I just wrote on this page. So let me get rid of that there. All right. Last thing we're going to talk about is actually in this chapter here, molecular geometry. Not molecular geometry, molecular polarity. Now, earlier, if you remember, we talked about bond polarity. And bond polarity is typically where we use that difference in electronegativity values. So you remember we have the chart that went from 0 to 4. We did some subtracting to figure out if it's a polar bond, a non-polar bond, or whatever it may be. Molecular polarity is what we are talking about, the entire molecule as a whole. So the entire molecule as a whole, whether or not there's a polar molecule, whether or not the molecule is polar, and that would mean that there's really overall still unequal sharing of those electrons across the entire molecule. Or if it is a nonpolar molecule, which means overall we will have some equal sharing of those electrons over the entire molecule. When we talk about a polar molecule versus a nonpolar molecule, we're talking about it in the same sense of a polar bond versus a nonpolar bond. If you remember, when we have a nonpolar bond, we have equal sharing of electrons. It basically makes that bond neutral, right? There is no positive side or negative side. When we have a polar bond, because of the unequal sharing of electrons, in that bond, there's a negative side to that bond and a partially positive side to that bond and a partially negative side to that bond. And that's the same thing with a polar molecule. In a polar molecule, there will be a side of that molecule that's more positive because of the unequal distribution of those electrons, and a side of the molecule as a whole that is more negative. So those meanings are the same thing. If you have a polar molecule, you will have what is known as a dipole moment. And a dipole moment is represented with that same arrow we saw earlier, where it points to the more negative side of the molecule in this case, and the back end that makes this plus is the more positive side of the molecule, not just the bond, but the molecule in this particular case. So polar molecules will have a dipole moment, and nonpolar molecules will not have a dipole moment. And again, the major difference between polar molecules and nonpolar molecules is this: nonpolar, neutral, no charge. Polar molecules, you end up with a separation of charge in the entire molecule where there's a positive side to the molecule and a negative side to the molecule. So this is basically like neutral over here. Yeah, no charge on that guy. All right, so how do we determine if something is going to be a polar molecule or a nonpolar molecule? Let us start with probably the easiest ones to do, which is a diatomic molecule. So if you have a diatomic molecule, it basically means you have just 2 atoms involved. And if you had something like H2 or F2, even O2, when we look at each of these things here, the bond between hydrogen and hydrogen will have a difference in electronegativity of 0, which means this is going to be a nonpolar bond, right? So this bond right here is going to be nonpolar. Same thing over here. The F and the F, if you did the difference in electronegativity, you're going to get a difference of 0, which means that that bond right there is also a nonpolar bond. And if you did the difference in electronegativity between the two oxygens, going to give you a difference of 0, which means this is a nonpolar bond. Now, the number of bonds that each of these guys have in this molecule, there's only one bond here, there's only one bond here, and there's only one bond here, basically. So because that is the only bond in this entire molecule, and it's nonpolar, that would mean that this would also be a nonpolar molecule. And this would also be a nonpolar molecule. And this would also be a nonpolar molecule. So if you have a diatomic molecule and the difference in electronegativity is 0, or a nonpolar difference, it's going to be a nonpolar molecule because the only bond in the entire molecule is a nonpolar bond, and that makes the whole thing a nonpolar molecule, equal sharing of electrons. If we switched it up and did our HF that we saw earlier when we did our difference in electronegativity, if you remember, the difference in electronegativity is like 1.9, which tells you that this bond right here is a polar bond. And because this is a polar bond, and because that bond right there is the only bond in this molecule, that means that this molecule is going to be a polar molecule because of it. And we could draw a dipole moment just like we did with bond dipole. And bless you. And that arrow would head towards the fluorine, which is the more negative side of this molecule in this case. So if you have a diatomic molecule and there's only one bond, and that bond is polar, it will be a polar molecule. So those are very simple to do. The bond polarity, the difference in electronegativity, is the same as the molecular polarity in this case. So polar bond, polar molecule, nonpolar bond, nonpolar molecule. Now, if everything was that simple, that would be awesome, but everything is not that simple, obviously. So let's talk about what happens when you have 3 or more atoms. When you have 3 or more atoms, you have to look at 2 things. Are there polar bonds? And you have to look at the molecular geometry, or the shape of the molecule. So let's take a look at the classic example of carbon dioxide. When we look at carbon dioxide and we look at it to try to determine, does it have polar bonds? When you look at carbon and oxygen, they're in the same row in the periodic table, which means they're going to be a polar bond where the oxygen is going to be more electronegative. So we do have polar bonds heading towards the oxygen. So the answer is, yeah, we got polar bonds. Exactly. So you would think that perhaps because it has polar bonds, this molecule would be polar. But what ends up happening if we look at the geometry, which we just did, that is 2 electron pairs, that is 2 bonds, that is a molecular geometry of linear, a straight line 180 degrees apart. So what happens in this particular case is they actually cancel each other out, and this molecule becomes a nonpolar molecule. Because if I took my pen, for example, and this is the geometry, basically a straight line, and I basically have oxygen pulling this way, but I have an oxygen pulling the other way, right? Equal and opposite. And I'm actually pulling on my pen, and my pen is going nowhere. I'm pulling this way and this way. Pen is going nowhere. They cancel each other out in this case. So because of the geometry here, even though it has polar bonds, the overall molecule is actually a nonpolar molecule, equal sharing of electrons, no dipole moment. Now, if you take a look at another example that we saw earlier, which was water, water also has polar bonds heading towards the oxygen. Now, in this particular case, the geometry of water is 4 electron pairs, 2 bonds. That's going to give us our bent, our V shapes. And what happens in this case is you have basically oxygen going this way, oxygen going this way. They're going to kind of meet at the top. And you could think if you had something like on a string, if you pulled it from the top, the whole thing's going to move. And they actually will add together and create a net dipole moment where the oxygen side is actually more negative, hydrogen side of water is actually more positive, and this would be a polar molecule because of that. That is because those dipole arrows, they are vectors, like in physics, they have direction, they have magnitude. I fell asleep at that point. I'm not sure what happened after that, but I woke up long enough to know that in some cases they add to each other, right? And in other cases they subtract from each other. And cases where they are moving in equal and opposite directions, they will cancel each other out. Or if they're heading right at each other, they will cancel each other out. But in some cases, they could add to each other. In the case of water, what you have happening is something like this, a little head to tail action, and they kind of add upwards in that way. So because of this, this is going to be a polar molecule. Nobody wants to do vectors and figuring that crap out, right? So there must be an easier way. So let's talk about really the easiest way you can do it in like 2 seconds, which is there are some geometries which are known as symmetrical geometries. And these are the molecular geometries we're talking about. For you guys, you don't have too many. You've got trigonal, planar, and tetrahedral. So if you have any of these geometries when you draw your Lewis structure, what they have in common is no dots on the central atom. And if all the atoms on the outside are the same, it will be a nonpolar molecule. They will cancel each other out. So if you had something like this, you draw your Lewis structure, you look at the central atom, I got no dots. I got everything on the outside is the same. It's going to be a nonpolar molecule. It's going to cancel each other out. By the way, it does have polar bonds, as the carbon-fluorine bond is polar. So this is, again, another one with polar bonds, but the geometry will cancel each other out. Now, if I took one of those fluorines and swapped it out for a hydrogen, and obviously I'm not drawing the dots on the fluorines, I will still have polar bonds heading in 3 directions. But what happens with the carbon-hydrogen bond in this case? Carbon-hydrogen bond is nonpolar, which means you basically got 3 guys pulling this way, nobody pulling in the opposite direction. If you think about like a rope, 3 people pull this way, the last guy's just going to come for the ride, right? And in this situation, if you have this geometry and everybody on the outside is not the same, it's going to be now a polar molecule. So this will be a polar molecule if no dots, all outside atoms, not the same. Now, that leaves us the other type of geometry, which is unsymmetrical. And for you guys, your unsymmetrical geometries is trigonal pyramid, angular, and bent or V-shaped. And what those all have in common is they have dots on the central atom. And if all the outside atoms are the same, it's going to be a polar molecule. So, for example, if we look at our NH3 here, I see dots on the central atom. I see everybody on the outside the same. Going to be a polar molecule. No doubt about it. Yeah. I take a look at the SO2. I'll just draw it up here. But it goes with the guy on the bottom. I see dots on the central atom. Everybody on the outside is the same. It's going to be a polar molecule. So what that leaves you in terms of geometry is only linear, which is a pretty easy one to figure out. Think of it like a pencil. If those guys are heading in opposite directions, they're going to cancel out. If they're heading in the same direction at each other, they're going to cancel. But if they're all heading in the same direction, not at each other, but if they're all heading in terms of the polar bond in that direction, it would be polar. So that one's pretty easy to figure out. So basically, you can pretty much do polarity, molecular polarity in a second. I kind of erased it, but by just looking at dots or no dots on the central atom. And so, for example, again, water, dots on the central atom, everything on the outside is the same, going to be polar. And that's probably the quickest way that you can do it. All right, that wraps up this chapter. A couple of things before you run out.